Hi, everyone. Today we're going to talk about robustness in meta-reinforcement learning. Unlike standard reinforcement learning, in MetaRL, we have not just a single environment, we have many different environments or tasks. And each time we get a new task, we need to adapt to it. And we measure our performance as the average return over all the tasks. Now, the thing is that sometimes the average is not enough. For example, if we only have a single task during test time, we might need to do well on this task, even if it's a hard one. Or maybe we have many different tasks in tests, but they correspond to different users. And we care more about angry users, not just about the average satisfaction. So in both examples, we're interested not just in the average return, we're interested in being robust to difficult or high-risk tasks. And as a result, we propose to use not the standard average return objective, but instead a risk measure objective called the CVAR, conditional value at risk, which essentially says take the average return over the alpha worst case tasks. And alpha is often something like 1% or 5%. Now, when we come to derive the policy gradient algorithm for this objective, we find out that since we only optimize for the alpha worst case tasks, we only use alpha % of the data, which is very sample inefficient. So to solve that, we present the robust meta-reinforcement learning algorithm, which essentially learns to identify which tasks are more difficult and oversamples them during training so that we become robust to these tasks without throwing away data so that we can become more sample efficient again. Now, if you're familiar with CVAR optimization in standard reinforcement learning, not MetaRL, you might worry that our method or policy gradient method suffers from biased gradients, which is a major issue in CVAR optimization. But as it happens, we show that in meta-reinforcement learning, the way we define the CVAR objective, its policy gradient algorithm does not suffer from biased gradients. So it is safe to use and it makes it much more practical algorithm. Which brings us to our experiments, mostly in Mujuku. In the experiments, we show not just that our method, ROML, achieves higher CVAR return, we also achieve returns that are way more robust to the different tasks, and in particular perform better on the worst case tasks. Specifically, we show that ROML identifies that hard tasks in our setup correspond to high mass of the agent body, and it learns an interpretable policy which is just leaning forward so that gravity can pull the agent forward even if the body itself is more heavy. Just to finish with a practical note, ROML is a meta-algorithm in the sense that you can take your own MetaRL algorithm and feed it to ROML and get a robust version of your algorithm. So you can keep your own framework, your own algorithms, just need to change the way you sample tasks during training, and then you get ROML. And you can see an example for that in our repo. And good luck, and thank you very much for watching.